So this first chapter, Discovering Nanosafety, aims to give you the first, let's say, the first key to understand what is nanosafety, what are the main key, and to share the same vocabulary for all the training session. First of all, the scale. What means nano? Nano is a word coming from the ancient Greek, meaning infinitely small. So we talk about nano for 1 billionth of, for example, nanometers means 1 billionth of a meter. That means that when you have a nanoparticle of 1 nanometer diameter, for example, you have the same difference in scale between these nanoparticles and an orange than between an orange and the planet Earth. The nanoscale is between 1 nanometers and 100 nanometers. Knowing that the eye perception is at 10 micrometers, that means that the nano world is completely invisible for us. That's why we need some help, electronic help, such as microscope, to see nanomaterials and all the nano worlds. Nanomaterials can have several origins that can be natural, such as, for example, ocean spray, forest fire, or volcanic eruption. So here you have, for example, the volcanic eruption of the volcano in Iceland. I don't know if you remember it in 2010. I will not try to pronounce the name of the volcano because it was too hard for French people, but I'm sure you remember that. So all of these are a natural way to find nanoparticles, nanomaterials. Then you have the anthropogenic nanomaterials. That could be either unintentional or manufactured. Regarding the unintentional nanomaterials, that means that we don't need them for their magic properties and so on. Just we generate them when we do something else. For example, when we go on flight, for example, on a plane, we generate nanoparticles. When we use power plant, coal power plant, for example, to generate electricity, we generate nanoparticles. When we use cars and so on in cities, we generate nanoparticles. So we don't need them. And there is the manufactured nanomaterials that are needed for their properties. For example, here, all these particles came from the OASIS project. For example, Bucky paper, which are layers of carbon nanotubes. Here you have nano-reinforced metallic alloy ingot. You also have some magnetic or flame retardant nanoparticles and so on. A little bit of history. You have to know that nanoparticles, nanomaterial were used before the 20th centuries, but without any knowledge of their existence. We use the prefix nano at the beginning of the last century, and it's only on 1704 that we use for the first time the term nanotechnology. So it's young science that rise thanks to the invention at the beginning of the 80s of the tunneling microscope, and then with the atomic force microscope. Thanks to that, we were able to see them, and it was and to characterize them, and then to use them. At the beginning of our century, nanotubes, graphene, and medical applications of nanocontainer were discovered. Let's go now on some definitions. So first, the standardized definition. According to the ISO 80004, nanomaterial is a material with any external dimension in the nanoscale. So we already seen that this nanoscale means between 1 nanometers and 100 nanometers, or having an internal structure or surface structure in the nanoscale. If we focus on the manufactured nanomaterials, you can find two types of nanomaterials. The nano object with either one dimension in the nanoscale, two dimensions in the nanoscale, or three dimensions in the nanoscale. Nanoplates, nanofibers, nanoparticles. Sorry, or the nanostructure materials. It's the internal structure or the surface structure which is in the nanoscale. You can find here aggregates and agglomerates, nanoporous materials, or nanocomposites. Regarding agglomerates and aggregates, what is the difference? The difference is agglomerates are a collection of weakly bound particles or aggregate or mixture of the two, where the resulting external surface area is similar to the sum of the surface area of the individual components. So you have here a little image. And aggregates are particles. They are not a collection of particles, but they are particles with strongly bound or fused particles where the resulting external surface area is significantly smaller than the sum of the calculated surface area of the individual components. Let's go now on the regulated definition. You may know that on June last year, the Commission update its recommendation on the definition of nanomaterials. The new definition is nanomaterials means natural, incidental, or manufactured materials. So we have seen that at the beginning of the presentation. We all agree. Consisting of solid particles that are present either on their own or as identifiable constituent particles in aggregates or agglomerates. So we have seen what that means. And where 50% or more of these particles in the number size distribution fulfill one of the following conditions. So it's quite important to have that in mind. The 50% or more of these particles in the number size distributions. It's the key point of this regulated definition. Now let's see the condition. First, one or more external dimension of the particle is in the size range 1 nanometers to 100 nanometers. So we have the same situation as in the standardized definition. But two other conditions are added. First, it's possible to have a fiber where two external dimensions are below 1 nanometers if the other one is larger than 100 nanometers. And for the plate, you can have two dimensions with larger than 100 nanometers if the third one is smaller than 1. You can also note in this definition that a material with a specific surface area by volume below 6 square meter by cubic centimeter is not considered as a nanomaterial. So it's quite new in this update of the definition. Now, let's see how we manage that. We have seen what are nanomaterials, but we are talking about safety. So how do we do? First, we have to say that nanomaterials are covered by the same regulatory frameworks as for all chemicals and mixtures. That means that CLP and REACH regulations should be, we should comply to this regulation with nanomaterials as well. That means that the hazardous properties of nanomaterials of substances have to be assessed and their safe use need to be ensured. Now, let's talk a bit about the definition of risk, hazard, and exposure. Hazard is the intrinsic property of an agent situation likely to have an harmful effect. For example, here you have a cliff, and the height of the cliff will determine one of the hazards. The exposure is the action to place a person or an object in such a way as to expose them to the effect of certain agent or phenomena. So here you have a walker, for example, on the cliff. And risk is the probability that the potential for harm is achieved under the condition of use and exposure. For example, the walker is falling down the cliff. Regarding nanoforms, there is no consensus on the hazard of a nanoform. So that's why we work on exposure to reduce the risk. So why there is no consensus on the hazard of nanoform? Because many physico-chemical properties influence the toxicity. For example, the shape, sphere, cube, tube, and so on, the dimension, the form, the surface modification, the physico-chemical properties, and of course the chemical composition as for the other chemical. However, we already have some information of classification for cancer risk, for example. In the CLP classification, so classification, labeling, packaging, regulation, the titanium dioxide is classified as carcinogenic potential for humans suspected since 2021. Regarding the classification of the International Agency for Research on Cancer, you have 3 types of nanomaterials which are classified possibly carcinogenic to humans: the carbon black and the titanium dioxide since 2006, and the multi-wall carbon nanotube of type 7 since 2017. However, you also have diesel exhaust, which is carcinogenic to humans with sufficient evidence for cancer lung, and all the other carbon nanotube, which are possibly carcinogenic to, which are not classifiable for regarding the cancer risk. Let's now introduce another notion in terms of hazard identification, the occupational exposure limit. The occupational exposure limit indicates the level of admissible exposure for a length of time, which is usually 8 hours, to a chemical or physical hazard that is not likely to affect the health of a worker. For example, here you have 2 examples of occupational exposure limit for carbon black and amorphous silica. What you can see here is that the value deeply depends on the country. For example, with amorphous silica, in Denmark, the occupational exposure level is of 2 milligrams by cubic meter, and in Germany of 4. And Ontario, in Canada, 10. So you can see that the value could varies a lot from a country to another. Now let's go on nanomaterials. There is no, let's say, regulated occupational exposure limit for nanomaterials, but there is some recommendation, and especially some recommendation coming from NIOSH, American National Institute for Occupational Safety and Health. You have, for example, 2 values for the titanium dioxide and the carbon nanotubes. Let's go now on the exposure. In exposure, as for other chemicals, there is 3 routes of exposure: inhalation, ingestion, and cutaneous. The ingestion route of exposure is not considered likely to happen in a workplace, thanks to, let's say, obvious hygienic rules, such as wash your hands, do not smoke, drink, or eat in a polluted workplace. Regarding the cutaneous passage, there is no consensus and research are still ongoing. But what we know is that inhalation is the main route of exposure for nanomaterials. How does it work? So you have in the respiratory tract 3, let's say, 3 levels of deposition for materials. The upper airways, mouth and nasopharynx, the trachea bronchus airways, and then the upper airways with the alveoli. So if you look into this graph, you can see that for 200 nanometers, you have the less deposited fraction of materials into the respiratory tract, and that between 5 nanometers and 300 nanometers, the particles deposit deeper on the deeper on the respiratory tract in the alveoli here. And then when you go below 5 nanometers, all the particles deposit mainly in the upper airways. This introduces a new, let's say, a new notion, the lung deposited surface area, which is the total surface of the particle deposited in the human airways, and that could be an interesting parameter for assessing health effect. So to conclude shortly on this first chapter on this training, so we have seen what are nanomaterials. We have seen that risk is a combination of hazard and exposure. We have seen that there is no consensus on the hazard, and so we need to reduce the exposure in order to mitigate the risk. Regarding the exposure, inhalation is the main route of exposure. So now we need to understand the mechanism of inhalation in order to reduce them. And that's why Sylvie will now present you all this mechanism. Sylvie, I will leave the floor for you, if you still hear me. Is it still working? Hello? And it seems that online it's working, but I am not sure. Oh, okay.
Okay, so thank you, Josephine, for this introduction to nanosafety. Now we'll move to the second part of this presentation, which will be on exposure assessment and metrology of aerosols. So, as Josephine just said, inhalation is the main route for exposure. So it is quite important to know how to measure, how to quantify, how to characterize the particles that we breathe, actually, and particularly at workplaces. So that's, oh, yeah. Okay. So that's what we're going to talk about in the next talk. So my presentation will be divided in two parts. First, we'll see the nature and the behavior of particles in the air, and mainly what differentiates the nano particles from the larger particles. And in the second part, we'll see the means that we can use, the instruments that we can use to detect and characterize nanoaerosols. So I will focus on aerosols, of course. So first, when we're dealing with a particle suspended in the air, it is theoretically subjected to three types of independent forces. First, there's sedimentation, which is actually inertia under the effect of gravity. There's thermal diffusion, also known as the Brownian motion, under the effect of temperature, and also convection. So that's the influence of air disturbances. And these three can be applied, or are applied to all types of particles. So talking about sedimentation and thermal diffusion, they both obey two laws, Stokes law and Fick's law. And so these laws will provide the sedimentation velocity and the mean square displacement as a function of the particle size. And here it's a dp. It's the diameter, the equivalent diameter, which I'll be talking about in a few moments. And also you can see that we have to add a correction factor, which is the Cunningham slip correction factor, to be able to apply those mathematical models to particles which are below, which size is below 1 micrometer. So if you look at the mathematical expressions, you can easily see that sedimentation velocity increases with size, while, whereas Brownian displacement decreases with size. And if we're looking at, if we look at the nanosize region here, the nanosize range, then you can see that here we have the velocity in centimeter per second. You can see that sedimentation is negligible concerning nanoparticles. And actually Brownian diffusion here is not, well, has only a very small impact on the displacement of these particles. But there's convection, of course, which is a third action. So in occupational workplaces, we are subjected to ventilation, to the movement of people. Here on the left, you can see that an operator is working in a fume hood. And in a fume hood, actually, the air velocity in the front of the fume hood is in the range of 0.4 meter per second. So this operator actually is safe. And the powder that he is handling is aspirated in the exhaust ventilation. The capture of the particles actually depends on their size. Where diffusion dominates for small particles, capture will be quite efficient. But for large particles where inertia dominates, then the particles will not always be able to follow the airstreams, and so they will not be captured. Okay, so I would like to talk about a fourth phenomenon, which is coagulation. So we have seen that Brownian motion, actually, when it applies to one single particle, has only very small impact. It's almost negligible. But Brownian motion will cause collisions between the particles when we're talking about an aerosol. And these collisions will form agglomerates and aggregates. And there's an example here of a, this is an aerosol which size is centered at around 50 nanometers. And if we let it evolve here, you can see that after 4 minutes, its size has increased to 200 nanometers, and its concentration in number has decreased by a factor of 100. So of course, this well, the kinetics of this phenomenon depends on the initial concentration of the aerosol. So when for highly concentrated aerosol, it takes it takes 1/10 of a second here to reach half the initial concentration. But for aerosols in the concentration of in the atmosphere, so in this case, it will take more than 1 day to reach half the concentration. So from this, we can infer that the lifetime of a particle in the atmosphere will depend on its size. For small particles, coagulation, which we have just talked about, will cause the decrease of the concentration and the increase in size. So these are mainly non-intentional anthropogenic particles, as Josephine just talked. For coarse particles here in the micrometers size, which are from natural origin mainly, settling will be the main phenomenon and will cause the concentration to decrease. But for particles with sizes which size are in between, so between a few hundred nanometers and a few micrometers, what we call the accumulation mode, the main loss mechanisms are wet and dry depositions. But for these particles, these sizes, the deposition velocity, the sedimentation actually is quite slow, and interception by raindrops is relatively inefficient. So that is why these particles can remain days or even weeks in the atmosphere. Another point when we're talking about metrology is the background. So from what we've just seen, we can see that the background will be quite important and variable. We'll have to deal with these natural and non-intentional anthropogenic particles. So in urban air, this concentration is usually between, well, actually a few thousands to 30,000 particle per cubic centimeters, and their size is usually between 5 and 350 nanometers. That's what we have here. So we'll have to, so this important and variable background in time and space, we'll have to consider it when we want to assess the occupational exposure to intentional manufactured nanomaterials. Okay, so as a summary and take-home messages, so the bad point is that in closed environments, nanoparticles will stay longer suspended in the ambient air than larger particles. That's because the effect of gravity is negligible. And so it can take several days to a nanoparticle to settle via sedimentation. But the good point is that coagulation will prevent high concentrations of nanoparticles in the air over long periods of time. And another good point is that in open environments, the nanoparticles will be carried away in a more significant manner than larger particles. That's the effect of convection. And also at workplaces, the nanoparticles are captured by exhaust ventilation quite efficiently and more efficiently than larger particles. So now we'll switch to the second part of my presentation with the means, the detection and characterization of nanoaerosols. Okay, so first we have to start with a question, actually, which is the question of the issue of metric. What metric should we use to quantify airborne particulate matter? Here on the left, you have a graph that shows the normalized concentration as a function of particle diameter. And so this is one single aerosol, which is composed of two populations. The first one is quite highly concentrated, and it's around 100 nanometer in size. And the second one is much less concentrated, and it's 3 micrometers in size. So in black, you have the number-based size distribution, which is the metric that we use for regulation purposes. In blue, you have the mass-based size distribution, which is the metric that is used for occupational exposure limit values, as Josephine showed before. And in red, you have the surface-based size distribution, which is the metric that best correlates with reactivity, toxicity, and health effects. The lung deposited surface area, for example, appears to be the most relevant metric for quantifying exposure. So actually, there's no such thing as the best metric. So the metric we'll choose actually will depend on the question that we want to answer. And one last point is that the instruments that we're going to talk just in a few minutes, they provide or they yield the number-based size distribution. So these are the raw data from the instruments which we can rely on. And the other ones are always based on hypotheses. Like, for example, the density of the particles to obtain the mass-based size distribution. Another point is what we mean by size when we're talking about aerosol metrology. The instruments that we use, they do not measure the size of the particles directly. They actually measure some properties of the particles that compose the aerosol. For example, they measure the sedimentation rate of these particles. And the models, mathematical models, are all based on spherical particles. So that is why we're talking about equivalent diameters. An equivalent diameter is the diameter of a particle, of a spherical particle, that would have the same sedimentation rate, for example, here, as the real particle. So of course, if the real particle is not far from a sphere, it makes sense. But if we're dealing with particle or objects, nano objects that are one dimension, or two-dimension plates, or two dimensions plates or fibers, that doesn't make sense to talk about diameter. So we mustn't forget that instruments measure equivalent diameters and that the size will depend on what we call the size will depend on the method that is used for measuring it. So now, what is the principle of sizing in the metrology of aerosols? When we have a polydispersed aerosol, we need first to classify the particles by size. This can be done by inertia, by differential mobility, or by diffusion. And then we have to detect the particles, and this can be done by using electrometers or condensation particle counters. And if we couple these, then we obtain granulometers that will give the size distribution as the one I showed a few slides before. So I'm going just to give a little more information on the principle of the LP, the electrical low pressure impactor, the scanning mobility particle sizer, SMPS, which are very commonly used in aerosol metrology. So SMPS actually is the combination of a DMA, which is a differential mobility analyzer that classifies the particles according to their electrical mobility, and a CPC that detects and counts the particles via light scattering. So what happens here? So here is the DMA and here is the CPC. So the aerosol is introduced here, and it's the particles are electrically charged, and then they are sent or aspirated into this column here, which is actually composed of two electrodes, two concentric electrodes. So when we apply here a potential between the two electrodes, the particles here will be deviated from the stream, from the sheet air stream, and only one size will be selected here and in the slot at the exit. So we obtain a monodispersed aerosol. And then, of course, by scanning the potential here, we can scan also the size of the particles that are selected here. Now, LP works totally differently. LP is a cascade impactor, and it classifies the particles by inertia. So again, the aerosol is introduced here. It is electrically charged. Particles are electrically charged. And then the polydispersed charged aerosol is introduced here in this column, which is composed of impaction plates. So the largest particles, the large particles will be impacted on the first plates, the upper plates, and the small particles, which will be able to follow the airstream, will be impacted on the bottom plates. Each plate is connected to an electrometer so that each particle that is impacted on the plate is detected. So this is a summary of the instruments that we can use. Some here are just counters, so they give information on the concentration of the particles, no information on the size. And the other ones are granulometers. So SMPS is actually the best instrument that we can use concerning the resolution, the limit of detection, the sensitivity, but it has one drawback, which is its analysis time. It takes several minutes to obtain one size distribution. LP is less resolutive. It has a lower limit of detection, but has one interesting feature is its analysis time, because each second it will provide, it will yield a size distribution. And this can be very interesting if we're dealing with transient events. Okay, so now we've seen the commonly used instruments. But if you remember, we were talking about the background. And the instruments that we've been talking about, actually, they just detect the particles, right? So they make no difference between a particle that comes from the background and a particle that comes from your experiment or maybe your process. So as we said, this background is important and variable. So if we want to detect, to have a low detection, we need to find some other, well, first we need to perform background correction. So that's the first point. And we also need to develop instruments, methods that are based on other approaches than just simple particulate detection. And this can be done by chemical analysis or by tracing also. And in this case, if we look, for example, at chemical analysis, so this will be the material detection. If you're working with gold nanoparticles or titanium dioxide nanoparticles, then we know that gold is not ubiquitous in the nature or in the environment. That would be nice, but it's not the case actually. So if you're able to discriminate or to measure only the gold particles from all the particles that are around in the background, then of course you'll be able to decrease the limit of detection in a very significant manner. Here's an example of specific detection. So that's filter collection. Filter collection uses small samplers. These samplers are made of a very small pump and cassettes here that holds a filter. So you will collect the aerosol for a certain time for 1 day or 1 week or even 1 month. And after that, you can take out the filter and analyze it. So maybe by microscopy, if you're looking at very specific shapes of the particles, or chemical analysis. Of course, this is a qualitative or quantitative offline analysis. So it's time average. There's no information on a possible acute exposure during transient events. So we've seen that we can use personal samplers. We can also use personal monitors. In this case, these instruments will give instantaneous measurement with, so this time a high time resolution. They can give information and determine the number concentration, also the mean size, not the size distribution, but the mean size. And some can even provide lung deposited surface area. So actually, as usual, I would say no single instrument can do it all. And in tricky situation, then we'll need to combine samplers and monitors. That would be the best compromise. So I'm almost finished. I just want to show you some additional information that you can find in this review articles or book chapter or guidance documents. And I guess that's it. So I will leave the floor again to Josephine for the last presentation of this session. And she will introduce some risk mitigation measures that we can use for with regard to nanomaterials. Thank you.
Hello again. Can you hear me?
Yes, we can hear you.
Thank you. And you see my slide as well? Okay, I hope you do. So thank you, Sylvie, for this explanation. So if I go back, we have seen that, again, risk is a combination of hazard and exposure. I think that you have understood now that this is a key point, that we do not have any consensus on nano hazard, so that we try to explore the exposure. We know now that inhalation is the main route of exposure, and Sylvie explained us how to characterize, measure the nano exposure. So now we are quite able to mitigate the risk, and that's the aim of this, the purpose of this third part. So first of all, you can have some direct and indirect exposure of nanomaterials throughout the whole life cycle. So from production, storage, and transport, then to the dispersion into the atmosphere and waste management, and so on. So the exposure could be to consumer or to workers. And in this presentation, we will focus on the workers exposed, on the risk mitigation for workers in occupational facility. So first, the main principle to be followed are the 9 prevention principles according to the Council Directive of June 1989, on the introduction of measures to encourage improvement in the safety and health of workers at work.
Sorry.
Yeah.
We don't see your slides changing.
Ah, okay. But you see them in full mode, or?
Slide 3.
Sorry?
Slide 3.
Yes. We are on slide 3 with the hierarchy of control. Is that okay?
Yes, thank you.
Okay. So this 9 prevention principles should be could be summarized in this hierarchy of control, which I find it more easier to present to you today. From the most effective to the least effective, first the elimination. So you need to physically remove the hazard. We will not use nanomaterials. The substitution, we replace the hazard. Maybe we will not work with nanomaterials, but with submicronic, for example. Then the engineering control. We will isolate people from the hazard. Administrative control, then change the way of people working. And last and least, the personal protective equipment. We will protect worker individually. This should be also summarized again in a word easy to remember: stop. Stop is for substitution, technical, organizational, and personal. In this presentation, I will focus in the technical and personal way to mitigate the risk, because substitution and organizational should be really studied case by case. Let's begin with the technical way, with the collective protective equipment. Collective protective equipment could be static, so that means that the protection is given by the equipment, or dynamic, the protection is provided by ventilation. And for example, for static protection, you can have a closed oven, closed reactor, closed bins, for example, or closed can. For provided by ventilation, you have the fume cupboards. Yes.
Josephine, we're still on the hierarchy of controls.
Okay.
On slide 3.
On slide 3.
Okay.
Yes, so now we see stop.
And now, are you on the fifth one? On the 5?
We still see number 4.
Okay, I think this is an issue with the presenting mode. So I will try it like that.
Stay in this mode, please.
Sorry?
Stay in that mode.
Yeah, I will do that. So static here, as I said, a closed reactor, closed oven, dynamic such as fume cupboard or a suction arm. But you can find some equipment between both static and dynamic, such as a glove box, for example. Or here you have, we call that the nano box. It was a box to cut nanomaterials. With the gray part is the exhaust, but with all the edges and so on this box, it was really difficult to clean it. So we do not use that. But you can have what is important to remind is you can mix static and dynamic protection. So I will focus on the ventilation, so the dynamic protection. You can have two types of ventilation. The local ventilation, where the pollutants are captured at the source, and then they go out through the exhaust, or the general ventilation, where the pollutants are dispersed in the room before being exhausted outside. You always need to favor the local ventilation and the containment of the source of danger. So now I will move on this slide. I will do it in the presentation mode because it will be easier to follow for you, and then I will go back. Let me know if you do not see the animation. So first, you need to surround the pollutants production zone as much as possible. So here, for example, the suction flow is higher than in this situation. So it's really important to surround the pollutants. The second one, do you see it? Is it working? Is to capture the emission as close to the source as possible. So you can see in this picture that if you multiply by 2 the distance between the source and the fan, you need to multiply by 4 the flow. So it's really important to be as close as possible.
We see no animation.
Okay, so I will let it like that. So the third one, so here you have the second one. The third one with the images here is to place the hood so that operators are not between the source and the source and the exhaust. So this way is better than this way. If the operator is between the source of pollution and the hood, remind that his nose is the first exhaust protection, and that's not what we want. Then you need to use the natural pollutants movement. For example, with this grinding example, you need to use the movement of the pollutant to capture them better. Then you need to induce a sufficient speed in order to capture all the pollutants. Then you need to distribute the airspeed uniformly in the capture zone in order to avoid the leakage at the edges. Then you need to compensate the air exhaust by air input. 8, you need to avoid draft and thermal discomfort. And 9, after filtering, the exhaust polluted air outdoors should be away from the fresh air intake areas. All this, once you have that in mind, it's quite logical, but it's useful to see it once. Then let's talk on filtration. How does it work? So please focus on the right side because I cannot use the animation. So you have different type of filtration. The EPA, efficient particulate air filter with a E. The HEPA with a H, highly efficient particulate air filter, and the ULPA with a U, ultra low penetration air filter. For each of them, you have an efficiency to capture particles. And this efficiency is, these values are provided for what we call the MPPS, most penetrating particle size, which is between 150 nanometers and 300 nanometers. So the more efficient for the more efficient one for particulate filtration is ULPA, but ULPA are quite expensive, so we use EPA, H13 and H14 for nanomaterials because they are sufficiently efficient. And furthermore, as we said that this value at the most penetrating particle size, that means that they are more efficient for nanomaterials than for particles between 150 nanometers and 300 nanometers. Here you have 2 examples of particulate filtration in images with here a bag-in, bag-out system. That so the filter is in this box. When you open the box, you have a sort of huge plastic bag which protects the filter, the workers from the filter. So it's possible to perform the change of filter without being exposed. So now that we have seen that regarding the collective protective equipment, how to design a workspace. First, you need to restrict the access. Then you need to think about floor and walls, easy to clean. You also need to think about the wastewater collection. All the rooms should be negatively pressurized in order to avoid any split or leakage outside. The filtration system should be easily accessible. You need to avoid high energy tools such as compressed air blower, brushes, and so on. And you need to choose wisely your equipment in order to have integrated exhaust, a complete vacuum system, and so on. So here you have, for example, a workstation for multiple weighing station. So here you have these two, here and here, with a wall suction here and a vertical laminar flow. This workstation is thinking to have a large circulation area, but as you can see, the worker should enter the protective equipment. So in this situation, the worker need additional protection, which are the personal protective equipment. I would like to remind you that the collective protection has priority over individual protection. Individual protection is considered only when the collective protection can no longer be active, and the individual protection is implemented only after the risk assessment. So let's begin with the skin protection. So for the skin, you can use first gloves that should be, for example, vinyl or nitrile. I would like to remind you that it is unadvised to wear gloves with uncovered forearms. And for the more contaminated environment, 2 pairs of gloves should be worn together. It's also important to change gloves during transport, change of premises, and so on. Regarding the body, you can use woven or non-woven lab coat, depending on the level of contamination in the air. And you can also have some protective forearms here, non-woven, if you only need to protect your hand and your forearms. But do not forget the other risk. You will see that I will repeat that a lot. When you want to protect workers against nanomaterials, you also need to think of all the other chemicals and other risks as well. So when you choose the gloves or the lab coat and so on, you need to think of all the chemical risk at stake. Let's go now on the respiratory protection, which is, let's say, the main, the more important one, as we have seen that inhalation is the main route of exposure in workplace. So you have 2 types of respiratory protection: the filtering device, CIS, for low exposure, and the breathing apparatus for significant exposure. So let's begin with the breathing apparatus. They can be autonomous or non-autonomous, and the idea is that they provide fresh air to the fresh oxygen to the worker. With the filtering device, the workplace air is filtered, and then the worker inhale the filtered air. You have 2 types of device: the power assisted filtering with a pump in order to help the worker to inhale. It's recommended when you work more than 1 hour with this kind of devices. And the negative pressure device is the workers that do all the job to breathe, and so it's recommended for work that take less than 1 hour. So let's go in detail in the filtering device. All the masks on filtering devices are done with the same way, with the air purifying element, the inhalation valve, and the exhalation valve. Regarding the air purifying element, the filter, it could be of 2 types: the particulate removing or the vapor and gas removing. Let's focus on, on the air purifying element. So there is a lot of different filters, and all of them are codified with a letter and the color. For example, the filters P are always white and are used for particles. The filters A are always brown and are used for organic gases and vapor with boiling point large higher than 65 degrees. So that's an example. Again, you need not to forget the other risks. That means that when you are choosing a respiratory protection for nanoparticles, you also need to think of all the other chemical risk possible in order to find the best combination of filters to protect the worker from all of them. Then you need to know that for all these filters, there is 3 classes, 1, 2, and 3. For vapor and gas, the classification is based on how much the filter can hold, with 1, the lower capacity, and 3, the higher capacity. For particles, so P, the white, the one which are interesting to us today, the classification is based on the filtering efficiency, with 1, the lower efficiency, and 3, the higher efficiency. So for nanoparticles, we used P3 filters, but we need to combine them with other if needed regarding your activities. I just want to remind you that to be efficient, a mask should be worn correctly. That means with an elastic on each side of the ears, and that having beard decreases respiratory protection efficiency. So this type of filtering devices with negative pressure devices are not working for people who have a beard. Now let's talk a little of operational and emergency. And regarding the time, I will be shorter on these points. The main idea is that for each task, you need to have a procedure and instruction where you identify who is in charge of the work and according to which modalities. Regarding the who, do not forget that for external company, you need to perform a specific risk assessment to assess the potential cross-contamination between your risk and the risk of the external companies. For example, another example of maintenance, you need to maintenance or clean an enclosure, a reactor. You need for this task to have an internal procedure or instruction explaining how to do that, because regarding the cleaning techniques you may use, the nanoparticles emission could be really different. For example, you will have less emission when you clean with a wet wipe than when you use a sanding machine, for example. Now, you also have to have in mind that you need to label and signal the activities with nanomaterials. So here you can find some specific pictogram that we have found in some companies or organizations. Here you have the one offered by the French Institute of Occupational Safety. And this kind of pictogram should be displayed on work equipment and on all facilities entrance. Regarding the the product handled, you also need to label that they are nano. So to do that in CEA, we use this pictogram, but it's only the CEA pictogram. It could be an ID for you as well, but what is important is to label the content of nanomaterials. Let's talk now on the waste management. So waste management go from production and collection sites to treatment through transport and transit and recoping center. So in this slide, I would like to focus on production and collection sites. And please do not forget to respect all the usual waste rules. So what is important is to separate them from other chemical waste, keep close garbage can as possible to the ending as possible. They should be tightly packed. You need to label them. The packaging should be double resistant and hermetic, and single-use leak-proof for the liquid. And you need to inform the collection companies. Regarding the time, I will I will skip the CEA feedback. And now let's talk on emergencies. In CEA, we divided emergencies with nanoparticles in two types. First, the minor events, when the events are restricted to the workstation. That means that you have small quantity, no victim, you stay in the fume cupboard or in the glove box or in the reactors. In this case, we have pre-established safety instruction to be followed by the operators, and it need to inform the hierarchical or security lines. We also predefine the PPE or instruction of cleaning and all the modalities to be implemented. However, if the events go beyond the workstation, spreading on the ground, explosion, airborne dissemination, the first thing is to make the installation safe. Then we have some procedure in order to help the personnel to exit, and they need to call the emergency services. Let's talk now shortly on the occupational medical follow-up. So here you have the directive which contain the main guidance to ensure the health surveillance of workers. And regarding nanomaterials, how can we do that? Knowing that we do not have any specific legislation, we do not have biological exposure index, we do not have occupational exposure limit value. So knowing that, the American National Institute of Occupational Safety and Health have provided guidelines asking to have an initial medical examination, to have periodical medical examination, to have more frequent and detailed medical examination when you use nanomaterials, to have post-incident examination, to train workers to recognize symptoms of exposure to nanomaterials, and to take action in response to identification of potential hazard using nanomaterials. The key point of that is to keep traceability of exposure. Okay, I will conclude now with some take-home messages. The key point of this 1 hour and 30 minutes presentation is you need to limit the exposure and to keep traceability of all of them, of all exposure. So from the more effective way to reduce exposure to the less effective, first you have the design of the product, of the workstation, all the design. Then you have intrinsic safety. Could you eliminate, substitute, or mitigate the hazard? Then you have the engineering control. You can work on process simplification and optimization. You can work on enclosure. You can work on isolation and containment. You can work also on ventilation. Then there is administrative control. You can work on information and training, on procedures and work period, on housekeeping and personal hygiene, on medical surveillance as well. And last and least, but really remember that, last and least, the personal protective equipment with respiratory, skin, and eye protection. All of these this main point we have seen should be during all the life cycle of the product in your facilities, from the introduction to the outside, with the use, obviously, but also with the storage, the transport, the elimination, the maintenance and cleaning, maybe the recycling activities, and so on. You need to think with all the tasks. You also need to involve workers on all these tasks regarding safety. And for all these tasks as well, you need to imagine the potential emergency and to pre-establish procedure and instruction of what to do in case of emergency. So that's it for this presentation, and I think we succeed to keep the time even with our difficult beginning, but I hope this will help you in your future activity. And in case you have any issue, do not hesitate to contact us.